CBT Nuggets JNCIS Security Series IPsec VPN Part 1. Well, one of the most important duties you're going to have as a security officer or a security operator is to make sure that the resources and the assets at your corporate headquarters are able to be extended in a secure way to a wide variety of different sites and locations and remote users. That's where virtual private networking comes in. Now, the bottom line is VPN is a generic term to describe a wide variety of ways to create secure solutions to extend corporate networks over untrusted or unsecure networks. IPsec is just really one of several ways to accomplish this. It is, however, the most important function that we're going to be looking at here in the JNCIS series for VPN security, and it's going to be IPsec or IP security, which, by the way, is an open, extensible standard. In this first nugget in part 1, we're going to really focus on IPsec in a general way, in a generic way, not the SRX specific or Juno specific or Cisco specific or whatever. We're going to look at IPsec as an open global standard. Then in part 2, we'll get into the SRX distinctives. Sound good? Okay, let's dive in. You know, for a second, let's just talk about what it's like for the normal user who comes into the office on a daily basis. Not you as an administrator or some type of manager of a security system or the network, but just a normal end user. Think about what happens when you sit down at your desk at 9 o'clock in the morning at the corporate headquarters, which of course over here is Nugget Lab. So what do? Well, you check your email, right? Maybe you'll get into some productivity software like Microsoft Office or some other open source program that's running on Linux servers. Maybe you'll do some work and then save that to some file servers, for example. Maybe you'll query some databases to find out information, to do research. Maybe you'll update a database, make changes to that database through some front-end commercial or custom front-end. Maybe you'll access your intranet to find out, what's going on with the next holiday party or HR information. Maybe you want to find out what's going on in other departments. Maybe you're going to use Microsoft SharePoint to manage workflow on information in document libraries. Maybe you can do some instant messaging and do some chat or some video or send some files through Instant Messenger. How about some voice over IP, for example? Maybe some video conferencing. And then maybe before lunch you'll do an hour of training that you get as you download that from some streaming server. Now, these are just a handful of things that you might do at the corporate headquarters on a daily basis, a weekly basis. Well, how do we extend all of that functionality to, let's say, yourself when you have to go and work from home as a teleworker? Maybe you're a mobile user on the road. Maybe you're in a hotel room. Maybe you're at an airport, internet kiosk. Maybe you're a manager or a supervisor and you have to go to different sites like different branch offices, regional branch offices. Maybe you have to extend some of that information like part of the intranet or part of the database information, product information to one of your strategic partners. Maybe you have a large vendor or a large customer. Well, if you're going to extend all of those capabilities over public networks, it's going to be basically sent in the clear. It's going to be readily available for man-in-the-middle attacks, meet-in-the-middle attacks, no confidentiality, no integrity. Okay, it can be changed in process. How do you protect that information as you access back and forth between all these different types of sites and different types of remote users? Well, there's many solutions, but we're going to focus on the IP security or IPsec virtual private network solution. And so before we look at how we implement that on the SRX, which would be the device we use here at the customer edge router at the headquarters, as well as devices we deploy at partner sites, regional branch offices, small branch offices, teleworkers' homes, small office, home office, we want to look at how IPsec works. Now, why is IPsec so important to learn? Well, it's ubiquitous. In other words, it's everywhere. And there's an implementation of IPsec with pretty much every major vendor, whether it's Microsoft's RRAS or SonicWall, Checkpoint, Cisco. other vendors like Certus Networks or NCP Engineering, and then major vendors like Dell, IBM, and Symantec. They all offer VPN services, not just IPsec, but other VPN services as well. And IPsec is a framework, okay? So you can easily add functionality to it. It's extensible, so you can extend its functionality, extend its use over different types of networks. It's an overlay solution, so it can overlay a wide variety of different types of layer 2 connectivity, traditional WANs, as well as broadband connections and others. It worked with MPLS, multi-protocol label switching. It's very flexible as well, and a lot of vendors kind of have their own flavoring of it. For example, I can implement IPsec on a Cisco adaptive security appliance. I can do it on a Cisco router. I can do it on a Juniper router. I can do it on a Juniper SRX. I can do it in Checkpoint. And I understand the fundamentals of it, so there's some consistency across all of the appliances, but there are some nuances and some extra flexible things that are added on. And it's scalable. Relatively scalable in a full mesh environment or any-to-any environment if you use some of the newer extensible versions of IPsec. Now, since IPsec or IP security is an open standard, it has requests for comments associated with it. Now, the original RFCs in 1995 were 1825 and 1829. These were replaced in 1998, 3 years later, by RFCs 2401 and 2412. Now, by the way, these are the main RFCs for IPsec, but there's quite a few others that kind of fall into the extensibility and add other functionality that can be used by IPsec that aren't listed here. So 2005 we saw 4301 and 4308. The most common protocol of IPsec is encapsulating security protocol ESP, which provides confidentiality, integrity, and availability. It's covered in a couple of RFCs, 2406 and 4303. IPsec is so important that it was actually included natively into IP version 6. So IP version 6 has extension headers, and one of those extension headers is authentication header, the other protocol that we see used by IPsec. Two main protocols, ESP and AH. One thing about AH, it doesn't provide confidentiality through crypto systems. Okay, it doesn't encrypt and decrypt the actual message, but ESP will do that for us. So IPv6 really supports natively integrity mechanisms and authenticity mechanisms with hashed message authentication codes, or HMACs. An HMAC is basically going to take a cryptographic hash and add with it or seed it with a shared secret key. Okay, so the hashing gives us our integrity, and the secret key, which is shared between two peers. For example, the user at this teleworker office and this device here at the customer edge of Nugget Lab shares a secret key. That's where we get our integrity and authenticity of the peers. We'll talk more about that. But as you can see, this is a globally used security protocol and service and mechanism, and it's important to learn. And we have to really get our hands around it early on in our security careers with Junos. Now, there's two main categories of IPsec VPNs, and the first one of these categories is what we call the site-to-site VPN. And this can replace your traditional peer-to-peer links that you might have between, let's say, a government office and a university, your peer-to-peer WAN links that you might traditionally use using something like Frame Relay, for example, or ATM. Basically, what you're doing here is the peers or the participants in this IPsec relationship are devices, peer devices. So you'll have a VPN gateway at the headquarters or the head end, and then site-to-site connections with remote offices and branch offices down here, teleworker offices or SOHO, small office, home office, using, let's say, broadband connectivity with DSL and cable, maybe even using satellite. The remote office, branch office might be using broadband connectivity. They might also be using some other connectivity to the ISP or the point of presence. For example, ATM, Frame Relay, Metro Ethernet, things like that. Maybe you have extranet business-to-business partners, okay? And so those would be connecting in your site-to-site. The bottom line with site-to-site is each one of these particular locations has a device, some type of device that terminates the IPsec VPN tunnel. So the peers are actually devices at these other sites. That's why we call it site-to-site. And these newer site-to-site solutions using higher speed bandwidths, bigger pipes, using the internet and the points of presence on the internet means we can move away from our private WAN connections and our more expensive leased line connections and other older solutions to lower cost, lower total cost of ownership, have more scalable solutions, compatibility, because IPsec is ubiquitous, and of course it provides security. And in many regards, some of the highest level of security because you can leverage algorithms like, for example, AES, which is US government standard as a crypto system for encrypting and decrypting information. Now, one other thing about site-to-site that separates it from other VPNs is that typically we're not installing some type of IPsec or VPN software on these devices. Usually, the VPN or IPsec stack is part of the operating system. Okay, so it's part of Junos on your Edge router or on your SRX gateway. Or if it's some other vendor like, let's say, Cisco or SonicWall, it's in the operating system. So the device has it embedded into the operating system as a feature, a security feature. Now, when we look at our next solution, which is remote access VPNs, typically with remote access VPNs, you do have to install some separate type of software, especially on the client side or the remote side. Now, remote access VPNs are really the next generation of using older legacy technologies like the plain old telephone service or using, AT&T, your telephone service, or ISDN. Okay, and adding authentication services to that and possibly some encryption services. So this is really the new way to support telecommuters, mobile users, some of our business to business or consumer to business traffic where we have remote access users, people that are traveling. Okay, they're in airports or in hotel rooms, they're in their homes sometimes, but they're back in the headquarters sometimes. They bounce around from remote office to remote office or branch office to branch office. In the past, if you've been around a while, you knew that we would use like this dial-in software, with modems and possibly ISDN as our solutions that created these kind of circuit switch networks that we could kind of bring up and then tear down. They were really expensive, and with the advent of newer things like DSL and cable and satellite, and even using mobility solutions like cellular, we don't really need to use that anymore. Okay. So with remote access VPNs, what we're talking about is individual hosts, individual users who are installing software on laptops and operating systems and pads and mobility devices and basically accessing this remotely. Now, in the remote access category, it also brings up another option. Okay, so we can do IPsec remote access VPNs, right? We talked about that's one of the other types. But then we have other solutions if we don't want to use IPsec. We can use secure socket layering transport layer security, or SSL TLS. This is the software solution that's used by your web browser when you go and you access, you log on to CBT Nuggets or you go to PayPal or Amazon and things like that, right? So SSL TLS is what we call SSL VPN. SSL VPN is actually a different service than IPsec. Now, do they use some of the same algorithms and mechanisms? Yes, they do. Okay, even though SSL VPN typically will have other options as well because it's more kind of spread out globally over the internet. So SSL VPN is not the same thing as IPsec remote access. Let's just keep that in mind. Usually with SSL VPN, we're using it to protect pretty much web-based activities. Okay, think HTTP, right? That's why it's called HTTPS. Now, can you do some other things, putting on add-ons and applets and other smart tunneling type things to extend it? You certainly can. But with IPsec, it's basically any IP traffic. Okay, so that's one of the big differences between IPsec remote access and SSL VPN, or you might hear it called web VPN. Okay, is that it's typically web-based with some additional plugins or add-ons, where IPsec is any IP traffic. Okay, big differentiation. Now, usually in the world of SSL VPN, we break this up into two categories, which is clientless, which means you don't really install some VPN client. You're just going to use some supported web browser like Mozilla Firefox, Internet Explorer, Safari, or one of the other ones out there. The other type is client-based, where you're actually going to use some type of client, okay? So various vendors have their own custom clients that they can use, or you can have VPN clients that are built into the operating systems that you can use. Now remember, this is all under the umbrella of remote access, right? We're talking about remote access right now. So we have a clientless based solution or a client based solution using SSL VPN, okay? If it's IPsec remote access, okay? If it's IPsec remote access, then the software can be built in at the headquarters or the head-end device, but these remote devices, the workstations, the laptops, the pads, the mobile devices, whatever, they need to have some type of IPsec remote access client installed on it. Okay, it can be open source, it can be third party. There's a ton of them out there. Okay, so keep that in mind. Now, from a Juniper standpoint, there's different types of IPsec architectures. Okay, so I'll just put IPsec. These are architectures or their topologies. The classic one is the site-to-site IPsec VPN with site-to-site. So I'll just put S2S. You're typically configuring two sites to connect together. Okay, this can be a headquarters or a head end. Over here, H. And this can be a remote office, branch office, RBO, okay? Or it doesn't have to be, it can just be two branch offices, two satellite offices we want to connect together in a site-to-site way. Usually in these site-to-sites you have some type of backup link if the major link fails. That might be even a dial-up modem or an ISDN connection, okay? Or even a satellite connection. Another kind of architecture is what we call hub and spoke, okay? So I'll put H and S. A hub and spoke definitely has a head end or a headquarters device, right? Then it connects to two or more spokes, okay, which are branch offices. Now, in a hub and spoke, what makes this a pure hub and spoke environment is that there is no traffic. There is no direct tunnel created across this cloud, which is a service provider cloud, to spokes or the remote office branch offices. They do not have connectivity between them, right? So the connectivity, all the traffic, unicast, broadcast, multicast, always goes back through the hub or the headquarters. Why would you do that? Well, at the headquarters, you might want to make sure that you implement all of your policy, and these could be all going to a DMZ, for example, at the headquarters. All of the policy, all of the URL filtering, all of the routing, okay, all of those services, quality of service, for example, or class of service, all of those things are being handled at the headquarters, right? It could even also be your voice over IP, all going through the headquarters gateway, right? So that's a hub and spoke environment. Now what you'll see beyond that is like a hybrid or a multi-point VPN, where some of these will actually have communications between them. That's a possibility. What you're seeing happening more often than not now is that you have what we call a full mesh topology, okay? A full mesh topology. Regardless of whether this is the headquarters or not, the full mesh is allowing for any-to-any communication, okay? Now, why do we need this any-to-any communication now? Well, voice over IP, for example, to be able to rapidly extend the intranet and other services across all of the different sites. Conferencing, video, streaming services, voice over IP, all of these services that we need to have high connectivity, high availability, low latency, all those issues. You know, telephone services is one of those very important any-to-any communications. And if you're going to extend this and you're going to go ahead and packetize and use voice over IP across all of your different sites, all of the different areas of your corporation that are spread out over a metropolitan area, then you want to have this full mesh connectivity. Now, there are extensions of IPsec that are available in Junos and others like Cisco that are making this possible. It's called Group Encrypted Transport, okay, GET, G-E-T. So we have new extensible solutions that vendors like Juniper can use to create this any-to-any full mesh across all these different players, and it uses IP version 6, which is pretty cool. Okay, remember IP version 6 has authentication header built into it, so that's what we're seeing in creating these any-to-any communication. So there's all different types of architectures and topologies, and so kind of be aware of those. Now we need to look at some of the kind of the concepts of IPsec, the protocols, the algorithms, the mechanisms. We really need to define those. Okay, so let's start out first of all looking at the two main IPsec VPN protocols. The first protocol is Authentication Header, or AH. It's IP protocol 51, so it will populate the IP protocol field in the IP header with the binary number 51 if it's AH. You use AH when you don't need or it's not allowed to have confidentiality in your deployment. So it doesn't encrypt and decrypt. It provides integrity, it provides authenticity. It does this with hashed message authentication codes, or HMACs, okay? Either the MD5 or the stronger SHA-1, SHA-2 or higher. It's less widely deployed than ESP, encapsulating security payload, the other protocol, because ESP does it all. It provides integrity, it provides authenticity, and it encrypts and decrypts. It provides confidentiality. Now, authentication header is still used. It's a integrity mechanism that you see natively in IP version 6. We also use authentication header inside of an organization or a campus when we want to provide integrity, authenticity between front-end and back-end servers, or between host and servers in the data center or the server farm. You don't need to encrypt it. You just want to make sure there's integrity and authenticity between the different peers that are communicating. The more common choice is to use ESP encapsulating security payload, which is going to be number 50 in the IP protocol header. It'll encrypt the packets between the peers. So it takes the information, the payload, and it converts it into ciphertext. And we have several options for the encryption algorithm we're going to use. It authenticates the inner packet, which is the data, along with the ESP header. So it authenticates that portion as well. It offers data origin and data authentication. Remember, this is data origin and data authentication of the peers, not user authentication. Okay? If you want additional user authentication, then basically you need to extend the functionality and add some processes to your IPsec implementation. What we're creating here, by the way, whether it's point-to-point or hub and spoke or point-to-multipoint or full mesh, is security associations. And these authentication header or ESP security associations are unilateral. In other words, if you're going to have a peer-to-peer, right, then you need to have a security association, or SA, between the headquarters and the remote office, and then also one between the remote office and the headquarters, okay, unilateral. Now, even though the encryption that ESP adds is using more processing power, it's almost negligible today with the faster routers and appliances we have. So we typically always use ESP over untrusted networks. There's also two modes that ESP and AH can operate in: tunnel mode and transport mode. To keep it simple, tunnel mode we usually use between two endpoints, right? Two point-to-point. The headquarters router and the remote office router. The headquarters SRX and the branch office SRX, right? Or two servers. A Microsoft RAS server at the branch office and a Juniper router or SRX at the head end. Okay, transport mode is usually when we're involving some client to server environment where you have two laptops that have an IPsec tunnel together, or a laptop and a server. So in transport mode, the original IP address is going to be maintained. Okay, that's the important thing. With tunnel mode, though, you have an additional IP address that basically is the outside address of the peers, right? The headquarter router and the remote office SRX device. And the inside, or the original IP addresses, kind of becomes part of this inner packet that gets encrypted and authenticated. And it's because of that behavior with tunnel mode, whether it's AH or ESP, that we have to use some trickery to get around network address translation when NAT is being used along the path. Because remember, the original IP addresses are kind of being encrypted or encapsulated. So we have some mechanisms to kind of take that information and extract it and make it available so we can get through routers that are doing network address translation or port address translation. Okay, before we go any farther in this series, I want to recommend to you that you go to YouTube and do a search for Art of the Problem. This is Britt Cruz up here. You can see Britt Cruz. He has several excellent little movies on cryptography. I want to highly recommend that you go and if you could, even stop right now at this point in my Nugget series and go spend a little bit of time going through his easy to understand tutorials, and not very long, on crypto systems, cryptography, asymmetric keys, Diffie-Hellman, those kind of things that are really important. I don't have time to, go into what you would cover, let's say, in a Security Plus or a CISSP here in this Junos series. So pause me and go take a look at this, or once we finish up this first nugget, go up and spend some time going through these movies at YouTube. Now, IPsec uses various cryptographic algorithms to provide different services. The main service that it provides is to basically encrypt data, to encrypt information, not just the ultimate payload in the IPsec tunnel, but also to encrypt activities that happen to set up and negotiate those tunnels. So what we do is we obfuscate the traffic into some ciphertext, and we do this primarily with symmetric key algorithms. Now, a symmetric key encryption algorithm means that both sides share the same secret key. That secret key can either be generated by administrators and shared through some out-of-band format, or it can be generated using some other mechanism, for example, like Diffie-Hellman. The bottom line is you get two keys that are identical that are used to encrypt and decrypt data. The original protocol was DES, and this one has actually been cracked. So any new security implementation, you want to avoid DES if at all possible. It depends upon the devices you have as your other peer. Okay, if it's an older router or an older firewall, you may have to use DES. You typically want to use the newer version of DES, triple DES or 3DES, more powerful. It goes through 3 different rounds or 3 different iterations where basically you're doing triple DES EDE where you encrypt. That result is then decrypted, and then that result is then encrypted. Triple DES is considered trustworthy. You can have confidence in it, and it's one of the 2 choices you should use, the other choice being AES. Now, typically what you're seeing is we're using AES almost exclusively if you can. It's the most common one, is the US recommended. It comes in different bit links, AES 128, AES 256, and AES 384. Okay, I don't like this pin very much. Let's try this one. Okay, there we go. I had a weird pin going on. So you have AES 128, 256, 384. This is the key space. Okay, this is the bit length. So this is the number of possibilities. So for example, in the entire AES 128 key space, you have 2 to the 128th possibilities. That's a huge key space, where DES has a much smaller key space, like 2 to the 54th power. It's much more susceptible to brute force attacks. As a matter of fact, it's been cracked. Now, we also have asymmetric key systems. These are used in public key infrastructure and digital certificates and digital signatures. If you want to authenticate peers without sharing a secret key, you can do this with the certificate service, or PKI. RSA is kind of the public standard we use on the internet and with corporate environments. The government uses the DSA standard, okay, asymmetric keys. What that simply means is you have a public key and a private key, okay? And you can use the public key to encrypt, then you would decrypt with the private key. If you decrypt with the public key, you would encrypt with the private key. So, and by the way, those videos I showed you up on YouTube, they'll explain in better detail how this asymmetric crypto system works, and so make sure you do your homework there. Diffie-Hellman is also an asymmetric key crypto system, and it was actually a competitor with RSA. It didn't win, but they figured out that Whit Diffie and Martin Hellman figured out we can use this actually to generate shared secret keying material between 2 peers over an untrusted network like the internet. So you can actually use the Diffie-Hellman algorithm to create a secret key between 2 peers without a third party meet in the middle or man in the middle attacker being able to derive that. And so IPsec uses Diffie-Hellman for just that purpose. We also use Diffie-Hellman to generate these secret keys, but it's also keying material. So you can use those same original keys to create other new session keys. Once a security association expires, then you can start up a new one. You can use the same Diffie-Hellman keys and generate new keys. If you don't want to do that and you want to go through the Diffie-Hellman process again, that's called PFS, perfect forward secrecy, adding another layer to this process in IPsec. And then our authentication algorithms, which provide integrity mechanisms, making sure that things have not changed in transit. Okay, integrity and also authenticating peers is the authentication algorithm. Okay, and we have MD5, which should be avoided. It's also been cracked in a very specific scenario, actually going back to kind of this PKI environment. MD5 it's really interesting, used a bunch of Sony PlayStations to crack a certificate server and distribute rogue certificates. Okay, MD5. So you want to avoid that and use either SHA-1 or SHA-2 as your authentication algorithm. These are HMACs, okay, hashed message authentication codes. They combine a one-way cryptographic hash, which is kind of like if you take it's a one-way function using large prime numbers. It's almost impossible to reverse. So you take some information, you run it through the hash, and you create this message digest, this kind of fixed length digest. Then you attach that or append it to the message, sending it to the other side, and they do the calculation. If it's the same number, you know it hasn't changed in transit. Okay, so an HMAC will actually do the hashing, cryptographic hash, kind of like taking coffee beans, right? Coffee beans into a grinder. It's you can put them one way through there. Getting those coffee grounds back into the original form is almost impossible, right? So that's what a hashing cryptographic hash does. The MAC part of this is the message authentication code. That's the authentication part of it. So integrity and authenticity, and the MAC will actually use a shared secret key. Okay, so if it's been seeded or it's been combined, the hash, with a secret key, then you know it's authentic for the most part. You know it came from somebody who had that same shared secret key. Okay, so all these algorithms work together, and these are the important ones to know about: DES, triple DES, AES, RSA, DSA, and Diffie-Hellman, MD5, SHA-1, and SHA-2. Might want to do a little bit of homework on your own. Let's go talk more about the major protocol that we use in IPsec to get this done, and that's IKE, Internet Key Exchange, and the two phases, IKE Phase 1 and IKE Phase 2. Okay, so how does all this work, right? Well, to do IPsec, it's going to take two phases, and the first phase is kind of like the classic Get Smart cone of silence. Maybe you saw this in the movie as well, the cone of silence that Steve Carell used. But before the Chief and Maxwell Smart can communicate securely, they have to agree upon some way to get the information that they're going to use to create this tunnel securely. Okay, so this, in other words, deciding to use these plastic bowls and this tube of a certain length and to talk to each other, that is kind of like what IKE Phase 1 is. You set up the initial cone of silence. Okay, so the cone of silence is necessary because if we're going to create a secure communication between the headquarters and, let's say, this extranet B2B partner here, before we actually send the information, the data, back and forth in the IPsec tunnel, whether it's tunnel mode or transport mode, whether we send it in IPsec, which is basically IKE Phase 2, we have to agree upon the parameters we're going to use. Remember earlier I showed you the different algorithms? Are we going to use triple DES or AES? Or are we going to use a shared secret key to authenticate? Or are we going to use a PKI? If we're going to use Diffie-Hellman to generate shared secret keying material, well, for IKE Phase 2 or IPsec, what mode of Diffie-Hellman are we going to use? For integrity, we're going to use an HMAC? We sure are. Are we going to use MD5 or SHA-1 or SHA-2? What's the lifetime of this particular communication going to be? So we have to initially kind of decide upon and negotiate the parameters of our security association. And so IKE Phase 1 is going to be a two-way, okay, a bilateral security association to build this cone of silence, to agree upon the parameters and the attributes and the characteristics. Then IKE Phase 2, or the IPsec phase, Okay, that's going to be basically two unilateral security associations. Now, why would you have just a single unilateral IPsec association? Well, what if this was a branch office and all you did was just replicate sales figures or inventory information one way over here to the headquarters? Well, then you could really just have a unilateral IPsec security association. But usually we go ahead and we have both. Let's talk more about what makes all this possible, and that's Internet Key Exchange. Internet Key Exchange is a protocol like ESP and authentication header protocols. It's part of IPsec, but it's actually made up of several mechanisms that it's not important, but it uses things like ISACAMP and Scheme and Oakley. It uses a wide variety of different mechanisms, but this protocol in general basically is going to help us authenticate peer systems to each other. It also allows us to generate encryption keys and keying material, and we can use that keying material to generate new session keys or new security association keys going forward. It also allows us to automate the key exchange process. We can automatically negotiate security association parameters. We can auto-generate or refresh keys automatically. Or if we want to, we can go ahead and do it manually. IKE allows us to do that. Now, there's two versions of IKE. Now, don't get that confused with two phases of IKE. Yes, as I mentioned, IKE has phase 1, the cone of silence, and phase 2, the IPsec security association, where the actual data is transmitted. But it also has two versions, okay? For years you've used IKE version 1. It's everywhere. It's ubiquitous, okay? As we're going to see, there is an IKE version 2, okay? But it depends upon if you have a new version of the Junos operating system as to whether your SRX is going to support that. Now, IKE phase 1, which again is building the cone of silence, has two modes. It has a main mode, which takes 6 steps to agree upon the parameters, or aggressive mode, which cuts it down into 3 steps. It's a lot faster, but you don't identify the peer. So no peer identity with aggressive mode. So usually we would use aggressive mode over a more trusted network, right? Then IKE phase 2 in IPsec, we generally use quick mode, okay? That's where we're actually setting up the IPsec security association, where we're going to transform the clear text information into ciphertext, okay, using something like triple DES or AES. There's also a mode called GDOI mode. You might look at this. This is the other mode that you would use if you're using that any-to-any full mesh get VPN thing I talked to you about, okay? So, but we're really focused usually on main mode and quick mode. That's what we use over the internet. Now, as I mentioned, I want you to know about IKE version 2, the new version that has some improvements, quite a few. It's pretty new, okay, as far as being implemented into vendors' products. It overcomes several limitations of IKE version 1. It's simpler and it just has fewer transactions than main mode. It gets the job done quicker, okay? It also has stronger protections for denial of service attacks, which traditional IPsec is vulnerable to. It's more reliable, it's more flexible and extensible. It also provides a functionality called MobiKE, which is basically secure layer 3 roaming. In other words, it is a mechanism to help facilitate secure mobility solutions. And since everybody's using different types of mobile devices and pads and handhelds and newer types of devices, we need that in Internet Key Exchange. And because of mobility, we need something that's simpler and more flexible and more reliable. Okay, let's break down IKE phase 1 and IKE phase 2. And remember, this is not IKE version 1 and version 2. This is IKE version 1, phase 1 and phase 2. Okay, so in phase 1, we're going to negotiate the encryption algorithms and the authentication algorithms that we're going to use to kind of secure the communication. Okay, this is not used to protect the data. That's done in phase 2, or the IPsec phase. This is also called the ISACAMP phase, ISAKMP, because that's one of the protocols we're using here. What we're negotiating here are the things that are going to use to secure our communication channel, or what are we going to do to build that cone of silence, in other words. Then we establish a secure channel using the Diffie-Hellman protocol, DH. And by the way, if you go back to that website, there's a great discussion on Diffie-Hellman there. Third step, a peer ID is authenticated using either pre-shared keys, which is a basic method for just maybe a few hosts, a few peers, or certificates. And the certificates is a more scalable option if you have a bunch or several different locations, together with IKE identity. Now that's main mode, okay? If you do aggressive mode, the three-step thing, you don't do the IKE identity process, okay? Then in the fourth step, we're going to negotiate optionally things like NAT traversal. That is used to determine if there's a NAT router or a NAT device in between the two peers. If there is, we have to do some sorcery. Okay, we have to do some trickery to get that stuff across. Or dead peer detection. Are we going to use that protocol to see if the other peer is alive or not with keep alives? Okay, so we can negotiate those parameters as well. It's kind of cool how NAT-T works. You should go look it up. It uses this cookie. It's pretty cool. Phase 2, the algorithms that are used to protect the data are negotiated. Okay, so this is what we're going to use we're going to build the tunnel, and we're going to transform from clear text to ciphertext. Then in step 2, we're going to decide, are we going to use ESP, which is more likely, or are we going to use AH? Then in step 3, we negotiate some proxy IDs. These identify the traffic that's going to be encrypted. Okay, we have to negotiate those IDs. Sometimes those are randomly generated nonces. Okay, then we have fourth step, optionally perfect forward secrecy. If we want to have a stronger secure environment, we would do this Diffie-Hellman process again. Okay, we would redo Diffie-Hellman and create all new keys. Otherwise, in phase 2, we'll generate keying material from the keys created in phase 1 with Diffie-Hellman. Okay, so PFS just adds another layer of Diffie-Hellman on there to make it more secure, and you see that used in military environments, government environments, especially if you want to make sure that there's no man-in-the-middle attack or there's no compromise. If somebody gets a key and compromises a key, if you're using PFS, the next time you create a security association, it's a whole new Diffie-Hellman set. You don't have to worry about it. Now, notice I mentioned here the IKE identity. Okay, this IKE identity thing. What can we use to identify peers? That's kind of a good question, isn't it? Well, we can use the IP address. That's the most common method. In other words, what is the IP address of the peers outside, public interface? On our SRX probably gigabit 000. What is that outside public interface? What is the IP address? That's a common way to do it. We can also identify with host names, a fully qualified domain name. Definitely have to have, good DNS, robust DNS set up. You can also have a user FQDN. This is kind of used for transport mode, okay? And then we can also use distinguished names, DN. Typically, though, we're going to go ahead and just use the IP address. Okay, so that pretty much wraps up what I want to talk about just to build the fundamentals of IPsec. When we get to the next nugget, I'm going to start getting into the distinctives of IPsec on the SRX. Okay, so we're going to look first off at the SRX VPN types. Okay, what's specific to that? We might also talk about the flow processing as well. Where does it fall in the process flow on the device? And then of course we're going to go and configure it. And when we configure it, by the way, it'll help all these things kind of come together, because as I configure in the configuration mode, I'll remind you of what we're doing in this IPsec process. All right, excellent. Okay, in this JNCIS security series, we looked at IPsec fundamentals. That was our part 1. In part 2, we'll take up with the SRX or the Junos distinctives. I hope this CBT nugget was informative for you. I want to thank you for viewing.